It's great to be here today with Jackson Pitts, who I believe likes to be called Jack, who is a condensed matter physicist that I met at the Chino conference on the quest for a spiritual home. And I'm really looking forward to getting to know Jack better and also to talk about some condensed matter physics, since that's something I've never had an opportunity to talk about before. So Jack, could you get us started and just introduce yourself a little bit, maybe just a little bit about your background and then what you're doing now?
Sure. Well, I am, like you said, I'm a condensed matter physicist, and there are lots of ways to describe that. One of the sort of less helpful ways of saying what that means is that it's the physics that goes on that is bigger than a molecule and smaller than a continent. It's another way. Another way of saying it is it's the physics of many particles interacting together. And there are a couple of other areas where you have so-called many-body physics, but that's basically what condensed matter is. I did my PhD at UC Riverside, finished up in 2019, and since then I've been working for a startup which is in the field of glass manufacturing, but we're making use of microgravity on the International Space Station to make superior quality glass devices. So, but
Wow, how do you get that opportunity? I mean, wouldn't everybody
that
like
is
to have access to the space station?
that's quite a treat, and so been doing that for about 3 years since the middle of 2019, 2020. We got rolling on that, and been really enjoying that.
You don't have to go up there, do you?
I have not been up there yet, but I've been supporting operations up there,
Uh-huh.
and on the
Wow.
line with Huntsville as the mediator up to the station.
So when you were growing up, did you always want to be a condensed matter physicist or a fireman or what was it?
No, I mean, not condensed matter physics, but certainly space exploration, certainly astronaut was number one
Mhm.
at the beginning, and that persisted quite a while. The love of science, and especially science that was on the kind of physical sciences side, but especially physics, and you know got my hands on Stephen Hawking pretty early on, and other little silly references of that thing, but always had lots of interests. So that was one. But
Well, so how do you differentiate particle physics and condensed matter physics?
yes, okay. So particle physics is where you want to break things apart into the smallest pieces that you can possibly find, see what the world is made of, and determine what the governing interactions are for those elementary particles. And the elementary particles kind of get more and more elementary as the decades roll on.
Mhm.
Hopefully, that's the goal. Condensed matter physics takes a little bit of a different approach, where the starting point is from particles which you already understand pretty well. Condensed matter physics was originally called solid state physics. And it's called that because it was the physics of what goes on in materials, in usually solid materials. And solid materials typically, we think about things like
So particles that are already stuck together or
particles
interacting
already
together.
stuck together.
Okay.
Yeah. Um, and the kind of perfect, the archetypal solid would be a crystal. And when we talk about crystals, what we mean is something which has the molecules or atoms or ions spaced at regular intervals from each other in an ordered fashion in a crystal lattice. There are other things which we talk about being solids, which a condensed matter physicist wouldn't necessarily call a solid. Things like wood. Wood is so complicated, you know, it's cellulose, and it's really kind of a very, very unusual structure. So we're not really talking about that. We're talking about things where there's an ordered structure to where the atoms are placed.
Well, I mean, the obvious thing that jumps into my mind is that wood comes from a tree, which is a living thing.
Right.
Crystals are usually associated with non-living things, but there is this one crystal that's somewhere in between, and that would be the DNA, the crystal formation of DNA.
Mm-hmm.
So does condensed matter physics ever look at DNA as a crystal, or is that too much on the life side?
Sure. There certainly is, and there are other crystal structures which are studied in physics, which are on the sort of biophysics or biology side.
Mm-hmm.
One example, one class of those would be protein crystals, where the structure of the protein is analyzed through X-ray diffraction and other techniques. But certainly, anytime you have a repeated lattice structure, so DNA has that in a one-dimensional system, and it coils in on itself in ways which I really don't understand and which I haven't studied myself. So the exact techniques for DNA crystallography and scattering, I don't have that expertise.
Right.
But
I was just trying to figure out where the dividing line was. Well, as you're talking about crystals, a couple of things jump out to me from the article that I read that you sent me, which was a very interesting article.
Good.
One of the things that it said is that the large system is less symmetrical than the underlying structure would suggest. Symmetrical as it is, a crystal is less symmetrical than perfect homogeneity. And so I was trying to kind of imagine that in my mind. So perfect homogeneity would be when everything is equidistant from itself. Would that be perfect homogeneity? And then a crystal has some sort of structure which makes it less symmetrical than that other thing that is just like if I had a Rubik's Cube, for example,
right.
Would you call that perfectly homogeneous?
This is a great question. So this is a question about what physicists mean when we say symmetry. So what a physicist means by symmetry is we talk about symmetries as nouns, actually. But a symmetry is something which you can do to a system after which the system looks the same as before you did it. So if you were to take a Rubik's Cube and rotate one of the rows 4 times, and that is a symmetry of the Rubik's Cube, because after you've done that 4 times, you're back to where you started.
Okay.
If you were to take a cube which didn't have colors on it, then if you were to rotate it just 1 time, just 90 degrees instead of 360 degrees, that would be a symmetry of the cube, because if you did that while I wasn't looking, I wouldn't be able to tell whether you had done anything or not.
Right.
So in terms of the question of why a crystal has less symmetry than something that's homogeneous, if you were to take an ocean of water, and an ocean without the fish in it, but a whole ocean of water, and while I wasn't looking, you were to move everything 1 yard to the right, or to the right for you.
Mhm.
And then I turned my head back and took a look. I would not be able to tell that you had moved it at all. But you could do that with any distance, because I can't see the difference. The water is all water. You know, sure, the atoms may be in a different place now, but I can't notice the difference.
Mhm.
On the other hand, if you take, so with something like water, with something that's homogeneous, you're not going to be able to notice the difference no matter what you do to it.
So in that sense, homogeneous means everything is just all mixed up in there.
Everything's all mixed up. Yep.
Okay.
Yeah. With
But
a
a
crystal,
crystal has particular structure.
it has particular structure. So if you move it exactly by the distance, which is the ionic spacing, the atom spacing, then I won't notice. But if you move it off of that, then I will.
Mhm.
And if you rotate it by a certain angle, maybe I wouldn't notice it. If you think of a crystal which has, you know, some sort of a hexagonal symmetry, you know, you think about those, a crystal which grows in a geode or something,
Mhm.
where you can see that it has this this faceted structure. If you were to rotate it maybe by 120 degrees, or maybe just by 60 degrees or something, I wouldn't notice. But if you were to rotate it by 45 degrees, if you were to rotate it by 10 degrees, then I wouldn't have that same facet facing me
Mhm. Right.
as was before. So
Okay. So that, yeah, that helps a lot. Then the other thing it said was this asymmetry, um, the fact that, well, maybe that's too complicated, this one, because it's talking about the crystals and the dipole moment, which is, maybe we don't need to get into that. Another thing that came up was this idea that you were talking about things that are put together and things that aren't put together, right? I know people are always complaining about reductionistic science, but one of the quotes in that article is that synthesis is expected to be all but impossible. Analysis may be not only possible, but fruitful. And so I thought about it, and that in terms of synthesis is the putting together of something. Analysis is like the taking apart of something. So for a physicist, I think, I mean, I've heard that if you're talking about all those particles that are down at that elementary level, that it's hard to imagine how they get put together into structures that can move up the different scales, but that there is great fruitfulness in analyzing them down to that particle level, because then there's so much you can do with that scientifically to understand so many things in the world that allow us to have cell phones and space stations and all that kind of stuff, right?
right.
So I thought that maybe that showed that there was a positive reason for reductive science.
Yeah, I mean, there certainly is. And if you, this is the More is Different article by
Mhm.
Philip Anderson. And he starts out at the very beginning. He says, yes, we have to a certain degree embrace reductionism on some sort of metaphysical level, but that's not the whole story. Got it there? Yeah.
Yeah. So
May still be a topic of controversy among philosophers, but among the great majority of active scientists, I think it is accepted without question. And so certainly there is a great reason to look at smaller and smaller scales and see what the world is made of at smaller length scales, or higher energy scales, which is the same thing, but I won't explain why. But at the same time, Anderson is explaining in this paper why that's not the whole story, and why physics has to take other approaches when it comes to the many body problem, when it comes to interactions among many, many particles together.
So is the many body problem in condensed matter physics the same, roughly the same idea as the n-body problem in astronomy?
It's very similar. Yes.
You want to describe the many body problem?
Well, I mean, the many body problem is that you can understand the underlying interactions, the underlying principles which govern the motion of particles and the forces between them. But once you introduce more than 2 or 3, depending how you count, objects, you can no longer arrive at a general solution to the problem. By general solution, what I mean is you can't write down an equation that is in terms of simple functions that will say where these things will be later in time. There may be special cases, highly artificial cases where you can know exactly where things will be over time, but that won't work for the majority of the ways that the particles or stars or planets could be moving. And what that means is that a bottom-up approach is not usually sufficient as a method for solving many body problems. I don't want to give the impression that means you have to be top down all the way, but
right. Yeah, I mean, we've talked a lot in this little neck of the woods about the bottom up and the top down kind of having to work together in some sense. So one of the things he talks about a lot in this article is the constructionist hypothesis. And I think I've worked out in my head what he means by that, but could you just briefly go over what constructionist theory is? And then I want to ask you a couple questions about it.
Well, by that he just means writing down the so what you would do in physics is you would write down the equations of motion, which in higher level physics are equations involving the energy and derivatives of the energy. You would write all those down and you would solve a difficult differential equation involving many, many, many equations, and you would arrive at the answer. So that would be a bottom-up approach. It's in sort of the more basic level physics, it would be like writing down you sum up all of the forces of all of the particles, and that gets you how things are moving, and then you figure out how they're moving. But there are too many equations to solve, and the equations are too complex to solve them generally. So I think that's what he means by the constructivist hypothesis.
Well, I guess if I think of this in connection with the Christopher Fuchs video about Q-bism, one of the things that he talks about in there is that the debate is actually about the reality status of what the math shows. So you're doing all this math. Mm-hmm. Is that actually showing us, even if the math could be done in a way that would perfectly illustrate what all these bodies are doing in a given period of time or over a period of time, even if the math could be done that way? You have math. Do you have reality? I mean,
oh, well, So that's getting into the Fuchs video that I sent. I don't know. Do you want to get into that now? I think so. I guess.
Well, okay, let's back up to the constructionist thing. One of the things that
Right.
Anderson said was the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe.
Right. Exactly.
And part of that is he brings up the twin difficulties of scale and complexity, and that's part of the reason that this is true.
Yes. So I've heard Eric Weinstein talk about it like this, that if you're studying chess, then the particle physicists are trying to find out the rules of chess, how each chessman is allowed to move, how a chessman is taken off the board, what constitutes winning. That's what the particle physicists are trying to figure out. The condensed matter physicists are trying to figure out strategies for playing chess. And so the constructivist hypothesis that Anderson is talking about there is the idea that by learning the rules of chess, that's going to easily teach you the strategies of chess. And that's just not really the case. You need to know the rules of chess in order to know the strategy.
Mm-hmm.
But you're not going to be able to, there's no short path from knowing the rules to figuring out the winning strategies. And
yeah, I mean, that seems to be absolutely true in something like painting a picture too. You can read all the books you want. You can even watch all the videos you want about painting, but you don't find out anything until you pick up a brush and start painting. And you're a painter too, right?
I am.
Yeah. So you know what I mean.
Yeah. I do, but I'm also curious about your painting and your experience with that. So
well, I mean, one of the real anomalies with painting is that you never know what your materials are going to do until you're working with your materials. And I mean, one of my naivetes when I first started out, I started with watercolor, and watercolor is wonderful because just on its own, it will make all these wonderful mistakes that turn into happy accidents that you can actually use because the chaos that shows up can have patterns in it, and it can become quite useful. And I got very used to working that way. And then but at one point I thought, well, surely acrylic would give me more flexibility, more opportunities. So I thought I'm going to switch over to acrylic. But then acrylic has its own problems because acrylic does not give you any happy accidents. If you want happy accidents, you have to produce your own happy accidents.
Right.
Every mark has to be intentional. You can't just fail your way into something with acrylic. So then I thought, well, acrylic has its own problems because the way that it moves on the paper or on the canvas and the way that it affects the brushes, you have to have different kinds of brushes. And I mean, there's all these physical things that relate to the paint. So I thought, well, surely oil would be easier because it takes longer to dry. You have more time to work with it. Then you start working with oil and it has its whole set of problems.
Oh, yeah.
You keep thinking that you can find something. There's some magic in the material, but the magic isn't in the material. And I don't even think the magic is in the painter. The magic is somewhere else. What's your opinion about that?
Well, I mean, on the very superficial level, acrylic is the one that I kind of stay away from. I love watercolor and I love oils. But I don't do a lot with acrylic because of that, because it's so I mean, what you put down is there. I like having things mix around. I like the um, reticulation of the little of the pigments, the separation of the pigments, and granulation, uh,
Mhm.
which I think you can certainly get it in both watercolor and oils. So those are the ones that I mostly stick to. Um, but yeah, I don't know where it is when it comes to painting. I and I think a lot about the question of how much control to try to exercise over the paint, uh,
Mhm.
and what that does to the experience of painting. So sometimes I think I try to be a little bit more controlled than I should. Other times I just get totally exhausted with the attempt to be a little bit freer. I used to do more abstracts, and it got very tiring for me to kind of just like do the sort of data, toss something in, and uh,
Mhm.
but I don't know. I think I heard you talk a little bit recently about the task of working with those happy accidents or working with the with what is given by the painting in the early stages. What do you think
Well,
about
because I have I've over the years I've developed two ways of approaching painting, regardless of what medium I'm working in. One of the ways is to create a bunch of chaos
that? Mhm,
in one way or another, maybe layers and layers of paint. Sometimes I put texture on the canvas, and then when I float the paint over the texture, it'll flow different ways because the texture is on the canvas.
mhm,
Or when I'm layering one color over another, the texture accepts the color in a different way where the texture is high or low. And so that by itself will create some anomalies on the canvas. That's one way I do it. Another way I do it is I go in and I take an old painting that was a failure and I turn it upside down and I paint over the top of it. Um, Typically, if I want to do something representational, like a figure or a village scene or something like that, I'll take an old failed painting of something else, turn it upside down, superimpose my drawing on top of that, and then I'll start painting. And because that thing is already there, I have to fight against it.
mhm.
So I don't have white that I'm working against this mass of colors that
Yeah, yeah.
so it changes the way I see things. But on the
Mhm,
other kind, where I create this canvas, this chaos on the canvas, um, when I start working, then afterwards, over the years, I've internalized this set of elements and principles of design. So I'm not just throwing paint on the canvas. I have already an idea in mind about proportion and balance and color temperature and color intensity and how size should work and to what extent I want to use line or texture in a painting. And so I have this whole thing that I've
mhm.
done so much with this that it's completely internalized in me. I don't think about it except if I'm having a problem finding my way through a painting, I'll stop and then I can analyze it a little bit and say, huh, maybe I'm too half with the color temperature, or maybe I don't have appropriate, maybe I have too many elements in this painting and I need to scale back and have fewer elements, or those kinds of questions I'll ask myself as I'm working. But that enabled me I like to do figurative work, but I don't like fussy, perfect, representational figurative work. I like to look at it. I just don't like to paint it.
Yeah, yeah.
So it enabled me to do non-objective work and still feel like I was a part of the painting. It wasn't just I understand exactly what you're saying. When you try to do something that's just totally expressionistic, it can get very tiring after a while. It's just like, well, yeah, supposedly that's expressing something about me, but what's it expressing if I'm just throwing paint at the page, you know? Where if I've internalized some set of rules, let's say, like the physical rules that hold the particles together, if I've internalized that, then as I'm working, it's a natural part of my work, even though I'm not consciously thinking about it. Does that make sense?
It does. How how quickly do you try to resolve when you're going about it through the, well, either way, through the chaos way or through the upside down way? I've found that, I mean, I've done similar things in terms of putting down a few marks and you know, just to get started, and then try to kind of solve the problem that is created by that. But sometimes I find that I just start doing kind of predictable compositions that, and I feel like I'm getting in a rut, and maybe a little bit trying to fix things too quickly. Maybe, I don't know.
Well, yeah, I mean, I guess it depends on when you say you put down a few lines. It took me a long time to come to the place where I felt like I have to have an approach.
Mhm.
I mean, I went to a lot of different workshops with famous artists, and the problem with that is you come out of that workshop with work that looks more or less like the work of the artist who was teaching you the work, right?
Sure.
So I had to stop doing that for a long time so that I could develop my own style. And I don't really have a style. I mean, you can probably tell when you look at my work, everything I have, you've seen the introduction to my website.
Sure. And
You-
I've seen your website. Yeah.
yeah.
You
So
don't think you have a style?
I don't think I have a style. I mean, if you look at all those cello players at the beginning of my video, every one of them is a different style, but they're all cello players.
Mhm.
So at the most, I could say maybe that my style is, I don't know. I don't know. But I do think that there's something about the way that I use color that is idiosyncratic to me. So a lot of
Oh,
people
yeah, yeah.
say, yeah, a lot of people say that they can tell by looking at my paintings because of the way that I use color.
Well, that's what first came to mind. I thought, well, your colors all make sense together. So,
Yeah, yeah,
okay, I was including that in with.
yeah. And I mean, I'm thinking of people that have a definitive style, like you can talk about Picasso's blue period. All the paintings that he did during that period were pretty similar in style, or his representational period before he even went into the blue period was, you know, very classical representational. And then he went into his, you know, totally abstract with the different perspectives, where one painting would have 5 or 6 different perspectives in it.
Mhm.
And then he stayed with that style for a long time, and it was, you look at it, you knew it was Picasso, right?
Sure. Yeah.
Right. So when people get into galleries, they have a recognizable style, so that if a painting sells, when they take that one off the wall and they put another one in its place, people coming in know that's the same artist.
Mhm.
That would never happen with my work.
You don't think so?
No, I don't think so.
I
People come to my house. I used to do a gallery show once a year, and we'd move all the furniture out of the house and just fill the whole house up with art. And then a few other artists would be in the yard under tents and have their art up on, you know, panels and whatnot. And people who didn't know me would come in and they'd look at all the art and they'd say, "Oh, there's so many artists in here." Like, no, that's all my stuff. But it's just the way maybe I'm ADHD or something, because it feels like when I do a painting that I really love and I think, oh, that's it. I want to do every painting from now on just like that. And then I start on the next painting and then I think, yeah, but what if I did this instead? And what if I use that medium? Or what if I changed brushes? Or what if I held the brush further out like this while I'm working, or and the what ifs just kill me because then I'm off on some other trail.
Mhm. Well, I've started doing some more representational work lately over the last year or so. And what I've really been excited to find there is that I'm just I'm just painting the best I can, and not not really trying to reproduce what I've done in the past, just going with whatever I have found success with in terms of getting something that I like, and
Mhm.
um, and really just sticking with, and they're not, there are photorealists, and I'm not shooting for that, but I'm just trying to paint as well as I can what I see, and what I notice is across half dozen paintings, there's a pretty consistent style, and
Mhm.
it's kind of comes out with just it just happens. But I do think you have a style, but um, but I think a lot of that is the color for sure. Yeah.
Well, probably when I do figurative work and there's more drawing in it, you can see my drawing style
Hmm. Hmm.
because I'm definitely not photorealist, and I never learned anatomy, so my figurative drawings are naive at best, maybe. But I'm much more interested in the relationship between the figure or the form and the background.
Hmm.
I want them to interrelate with each other and push and pull so that in some of my work, my goal was I would like to be able to put my hand over the face of this person and have a person think that this entire painting was just an abstract painting. But when I take my hand away from the face, you'd immediately see, oh, that's where the figure is. So that a person coming to look at it would have to adjust their vision just a little bit in order to see what I wanted them to see. And I worked very hard at that for quite a long time. I guess I could show an example of one of those because it was a lot of fun to do those. And I need to bring up my website for that. I like this push and pull thing. Well, even this one is kind of like that. I was trying not to make the figure too obvious. So if you saw this from across the room, you might not notice that there was a figure in there.
Right.
But particularly in the lute player series, you see, I can't do it right here, but if you cover up her face and you just look at the rest of her body and the shapes and the background and everything, I guess the hands and the face give it away. But other than that, it's pretty much just an abstract painting. In all these lute players, I was working with that, trying to play with the background. Like in this one particularly, you can see that the background and the foreground they're the same
Hmm. Right.
value, they're the same intensity, pretty much the same play of colors, the same kinds of shapes that are working in there. But then there is that face that tells you, oh, wait, there's a lute player in there someplace. So that was kind of my goal with this whole series.
And you're still, whether or not you've got the figure, you're still working with the rules of composition. You're still
Yeah,
working with rules of color theory,
right.
and
Yeah,
yeah,
trying to get
all
the
those.
placement, I mean, there's the whole Fibonacci thing.
Mm-hmm.
So, I mean, like this would be the typical place here would be one of the typical four places that you could have the center of interest. I was also taking a class where every painting had to be of the same subject. So I had to do 20 large paintings, all of the same subject. So um, you're kind of limited as to what you can do if you've got this lute player.
Yeah, yeah,
So, but what that does though is it just gives you this burst of creativity because I don't want to paint that same lute player over and over and over again. So, what can I do to make it different next time?
right. Yeah,
know?
it's an exploration.
Yeah, so like this one was mainly in reds and yellows. This one's maybe mainly with the alternate triad of purple, orange, and green. But I also wanted to explore more of the Asian aspect of the line drawing and the old Japanese print style with this one. And I like exploring backgrounds that are kind of mystical, I guess. Yeah. So anyway, that was part of what I was working on there.
Uh-huh. Well, so figure in the form in the background, or the figure in the background, is one of the things which you end up thinking a whole lot about in my area of physics, because there in particle physics there is sometimes an idea that you want to get to the very bottom where there's no background. And I may be kind of straw manning here, but in condensed matter physics, you're still doing physics. You're still using the same tools that the particle physicists use, but always you know that there is a background. There is a crystal lattice, and so you're not studying the individual atoms of the lattice. Instead, you're studying the collective behavior of the lattice as a whole. And so there are things which happen on top of the crystal structure as the backdrop. These are some of those things that would be hard to anticipate from just knowing the equations of motion of the electrons and the ions, and you find that you have emergent phenomena, collective behavior, tons of words for these, similar in a lot of ways to words that are used in this little corner of the internet. Not too far from thinking about distributed cognition or something like that. But you have similar questions, like the question of when you're looking at ants and you wonder, well, now wait a second, what's really the organism here? Is the ant the organism, or is the colony the organism? And that's where, in my area of physics, you start to think about the background and understanding the object, recognizing what's worth calling an object. So sometimes you have things that are really worth calling an object, which are not among the typical things that you talk about in an elementary level discussion of physics. So you might have, and you've got the nuclei of the atoms, which for a condensed matter physicist, you just kind of leave alone. You just call it the nucleus. You don't look at what's inside of it, but you've got the nucleus, you've got the electrons, and that's what you have. But when you have lots of those together and they're all interacting, you might have other things. So you would have what's called quasi-particles, and that just refers to collective behavior which exists in its own right, but is not made up of or is not just one of those kind of elementary particles. So you can have little bits of, usually this is like a wave that is
form. They're sort of
sorry.
like
I didn't mean to do that. I didn't
No,
mean
that's
to
okay.
Keep going. So you have
Sure. So you have this whole zoology or taxonomy of these quasi particles, which show up, and I'm sorry, I'm just looking at the video.
Yeah, I'll explain this in a second.
Sure.
Yeah.
And this is not something that's particularly exotic necessarily for a condensed matter physicist, and for other physicists, they'll know what this is, but something that exists long enough for it to interact with other things. And that's kind of the key, is that you can have things that kind of show up and disappear, but if they show up and they survive long enough to actually interact with other things, then they're worth talking about.
Well, so when you're talking about the crystal lattice structure, and then you were talking about quasi-particles, I just thought about this video. I'm not going to play it now because I can't remember exactly where the clip is, and it's a long video. It would take us a long time to find it, but I wanted to make you aware of it. Have you heard of Sharon Glotzer? I believe she's a particle physicist, but she did this bunch of, you can tell she's talking about quasi-crystals here, but she did this research. This is from 2015, this talk that she did. So prior to that, she was doing research with particles. They were synthetic particles. And she did the research with a number of different shapes of synthetic particles. But let's just say one shape was spheres, little spheres. Lots and lots and lots of little spheres put into a space. They're synthetic particles, so there's no life in them or anything like that. They don't even have nucleus. I mean, they probably they have atoms in them, I suppose, but the synthetic particle itself isn't like it's got electrons going around the outside of it. There might be a lot of atoms inside the synthetic particle. Okay. So what they did was they put them inside a space, and then little by little, they removed space. So they, made the boundary smaller, smaller, smaller. And at a certain point, these particles would automatically arrange themselves into a crystalline structure. Mm-hmm. And her statement that she made in the video was, they're doing that on the basis of entropy alone. And I heard that and I thought to myself, well, that's not entirely true, because you interfered. You reduced the size of the boundary. And my experience with art is that the tighter that I make a boundary, the more creativity goes on inside the boundary. The tighter I make the boundaries for myself, the more creativity can go on. And I do think that there's something true about that at some level. But she did change the boundary. And so that's always seemed to me as though it wasn't exactly entropy alone. So I looked into more about this whole issue of particles and quasicrystals. And one of the things that I thought I learned, and I want to ask you about it, is that the particles are seeking each particle, I'm anthropomorphizing here, each particle is seeking the maximum amount of freedom or space that it can have within a given placement. Mm-hmm. So they'll arrange themselves in a way that each one can have the maximum degree of either freedom or space. Is that roughly true?
Yeah, that is. And I think that is probably a good image to use when thinking about entropic selection of patterns, of states, of phases of matter. Yeah, I think entropy gets a bad rap in the popular culture, because the first form of entropy that we encountered in physics was thermodynamic entropy, and it starts to become associated with disorder, and then you start talking about the heat death of the universe, and oh my, this is so bleak. But I don't think there's really a need for entropy to be quite so vilified. And entropy is a measure of how many different configurations on the small scale correspond to a particular way that we can observe things at the large scale. And when you have something that would be a very low entropy system would be one which, if you make any changes at all, is going to start to look different. A high entropy system is one where if you change something a little bit, everything's more or less the same. Did I say that correctly? Yeah, I think so. And so when
well, so basically what she was saying then is that by reducing the space, when they formed into a crystalline structure, was that a reduction in entropy?
No, likely it was an increase of entropy. And so this is actually what, well, I don't want to say that necessarily, but I'm thinking of the research which I did for my doctorate, which was entropic selection of a particular class of ground states. We found a phase of matter associated with which was arrived at due to its increased entropy, even though it was an ordered state. So there are some unusual circumstances in which entropy can actually drive you into, or drive a system into, an ordered state, which kind of goes against what the sort of popular idea of what entropy is.
Yeah, for sure. Yeah, that's really interesting. And did you come to a conclusion with your doctorate?
Mm-hmm. Yep. So it's a highly it's a funny system and hard to explain, but in a way it's like if you were to just let people choose, just randomly, oh, we're not going to assign seats on this airplane, we won't assign seats, so let's just, airplane's going to be 2/3 filled and people can just sit wherever. And you might think, oh, well, if people can sit wherever, you're just going to get some kind of a random distribution of people sitting on the airplane. But no, you're going to get people so that all of the windows and aisles are taken, but all of the middle seats are not, right? 2/3, what's going to happen. So there are certain cases where you can open it up to randomness, and people want a little bit of elbow room. And because of that, even though, the space inside each seat is still exactly the same, no matter which one you have, people want the elbow room, and that elbow room can kind of give you an ordering. You might say, well, so if it's something that is not, if she's saying that it's entirely selected by entropy, what she's contrasting that with is that none of these states are going to be energetically favored over others. So none of them are technically at lower energies. So none of the seats on the airplane actually have more space. But, if you hit some turbulence, then you get jostled out of your seat just a little bit, and you've got that elbow room beside you. So
this is what's so interesting, though, about scaling, right? Because you're using an example from human beings with agency and cognition and consciousness on an airplane, and you're using that to describe particles in a small space.
Mm-hmm.
And I get an implication from that particles are not just little dead rocks. Is that?
I don't know if I would go with you that far, but I would.
But you're certainly using that language.
Oh, sure, and I mean, one of my favorite aspects of studying physics, one of the reasons that I went into physics was because it's so ripe with with examples that you can bring in, yeah, that's something that you want to be careful with. And I wouldn't necessarily say that the particles are I wouldn't say that the particles have agency like the people have agency, but I just love having that really wide range of analogies to draw from. And
Well, I wasn't trying to say that, or that I wasn't trying to say that you were saying, or even that I was saying that particles have agency, but I do think there's something about this idea of freedom.
yeah,
I think there's something about
do
this
too.
idea of freedom.
I do too. Yeah, well, do you want to talk a little bit about that, about Q-bism?
Yes, so I was going to bring up that
Okay.
video,
Sure.
and I have a couple of clips from it that I wanted to.
Well, let me start out with the usual caveats and disclaimers and all of that, but not really. So I sent you this this video, which I thought was a really nicely made video about an interpretation of quantum mechanics called Q-bism, which is at a kind of a level for a general audience. And I like Q-bism because it's not deterministic. A lot of the real popular interpretation of quantum mechanics right now is the many worlds interpretation.
Mhm.
And I just think that there are so many things that I don't like about it. And I don't like them for my own reasons that I think are well-founded, but which aren't really necessarily related to the physics of it. I just don't like the philosophy behind it. I don't like the determinism of it. I don't like the many worlds idea. But I do like the ideas behind Q-bism, and that's not to say that it's right. And there are some reasons why some other interpretations may be really worth considering. But I just found this so refreshing, and so that's what I wanted to do.
So Cubism is basic, from what I got from this video, is quantum Bayesianism.
Quantum Bayesianism, which is statistics from the point of view of belief about the world, as contrasted with frequentism, which is the sort of classical idea of statistics, but that's really not getting into that's really not at play here as much, except belief about the world. And so Cubism says that quantum mechanics tells you your best path forward in betting on what's going to happen.
Yeah, one of the quotes he made was that we can bet on, this is from Oliver Wendell Holmes, who said, we can bet on the behavior of the universe in its contact with us.
Yes. Yeah.
So what does that mean?
It means that if you're setting up an experiment and it's a quantum experiment, you can use quantum mechanics to place your bets on how often you're going to get a certain result. And that quantum mechanics is the tool used to make those bets.
Okay, so here's this little piece I thought was really interesting.
Anyway, he says, well, what does it take to be a decision maker? Is that answered in this book? No, it's not answered in this book because this is a manual for decision makers. So it can't answer the question of where decision makers come from. You can study the calculus in it, but studying the calculus will never tell you the recipe for making the thing that is able to use this book. And so on the questions could go. Now, there's a hint of these questions in the debate on quantum mechanics when a cubist says, Our starting point is an agent. And let's say maybe David Chalmers says, well, what is an agent? You've got to tell me what an agent is. Well, from the point of view of us, quantum theory is a manual that agents use. So it's not going to be able to answer the question of what is an agent. So this is why I think this is an apt metaphor.
Okay, let's repeat this.
So I thought that was really interesting, that quantum theory is a manual that agents use. So it can't tell you what an agent is. In the same way that that book on statistics that he was holding was a manual for decision makers. So the book itself can't tell you what a decision maker is. It's used by decision makers, just as quantum theory is used by agents.
Mhm.
So did you have any thoughts about that?
I love that clip. And you know, as a physics student, doing undergrad or doing graduate work, when you're doing your classes, you do a whole lot of problems in quantum mechanics. And with most of those problems, there is a mathematical object which is front and center throughout the whole thing. And that's what's called the wave function. And it'll autocorrect to 2 words, but we all just write it as 1 word usually. But you know, it's the wave function. And it's this mathematical object. It goes into the Schrodinger equation and is used when you're trying to calculate expectation values for energy or momentum or any of that. And you use it so much on every single homework problem. And I think this gives us the idea, well, you know, eventually I kind of remember, not exactly the time, but I remember around the time where I started thinking, you know what? I think the wave function is what's real. I think that's what's real. And our experiences come out of that. And that's one step. And the next step is to realize, wait a second, the wave function isn't just in this little portion of space, but it, you know, the tails on the asymptotes go out really far. They might go out so far that they actually kind of cross off with some asymptote of a wave function from a particle over here. And so really, not only is the wave function what's really real, but the wave function is universal. There's only one wave function in the whole universe. And then you learn about more complicated things, and you learn about more complicated fields, and you know, so the wave function, you know, maybe you got to go up to other levels, but that same thought sticks with you, and you think, yeah, that's what's real, and it's universal. And those are the 2 ingredients that you need in order to arrive at the many worlds interpretation, the Everettian interpretation, which says that every possible outcome from a quantum experiment happens, and we just don't really have direct experiential access with all of those, and it's very exciting. And then you realize, well, it's entirely deterministic, it's static, and it doesn't tell good stories. It's got weird moral implications. Like every time I don't do something awful, I think, gosh, somewhere else I did something awful. And
That would be exhausting.
oh yeah, it's totally exhausting. But I think it's what comes about from doing tons and tons of quantum mechanics problems. You start to think, oh, well, I've done a lot of homework in quantum mechanics. You know what? I think that you don't want to think that all of what you've been doing is not real, and you start to kind of over ascribe reality to a very helpful and very interesting and sometimes fun mathematical object that you work with. But Everett was not a lifelong researcher, and he was a student and he did some research, but I don't know. I think that I think it's kind of the tyranny of the students who come up with the the many worlds interpretation, where it's just people who've done too many problem sets.
Well, he talks about this a little bit here. Let's take a look at this. Go over here to 3058, I think.
And, you know, already, long before quantum theory came along, there were a number of philosophers who argued that a deterministic universe, you might as well just say it's a universe in which nothing happens. Because everything now determines everything that's going to come later. So why even go through the motions of moving from now to later? They contain exactly the same thing. The present completely determines the future. Why bother going to the future? Just live in the present. Within the last month, 2 different philosophers have thought that Q-bism didn't have a stance on determinism. And I've written to them, pointing out, one of them was a PhD thesis from the University of Sydney. And I can't remember who the other one was. But I pointed out that in the very paper of mine that they cite, I have this statement and this statement and this statement.
This is the total nightmare for any PhD student.
Q-bism strongly embraces the idea.
You do not want to write your
that
dissertation and then have someone you cite come in. Sorry to interrupt, but you don't want to write your dissertation and then get an email from someone who you've cited heavily and say, "Hell, wait a second, this is not what I said at all." Okay.
Yeah, it's really bad. Just the very end of what he wanted.
Yes, I'm sorry.
This is this phrase again. Genuine novelty comes into the world. Genuine novelty is constantly seeping into the world.
Yeah. So anyway, the reason I wanted to play this clip is that it had never occurred to me. I've heard people talking about determinism, and I don't agree with it. I understand the argument, I think, and I don't agree with it. But I've heard people talking about it, but it never occurred to me when I heard them talk about it that the implication was that if everything is determined, then nothing means anything. Mm-hmm. And when he brought that up, I thought, oh, wow, no wonder people are so in distress all the time. If any action that I take was already determined by the past, but also any action that I take is going to determine my future, and there's no way out. I mean, it would be so bleak. I mean, ugh.
It would be bleak. Yeah, this is something I've thought a lot about. And there is, you know, one of the things that I think rules out determinism to me is, ironically, causality. Causality is one thing causes another thing to happen. Mm-hmm. And I think just about everyone who believes determinism says, well, yeah, one thing causes another thing to happen. But I think that actually that totally rules out determinism. If you really want to keep causality, you can't have determinism. And the reason for that is because in a fully determined universe where everything is determined, then there is no reason to ascribe more causality. So let's say, you know, in 2023, on July 19th, something happens. There's no reason in a fully determined universe to ascribe any more cause to that thing happening on this day than any other point in time. No, if everything's so completely locked in, then I am who I am just as much from, you know, someone in Iceland I've never met as I am from my mother. And now, of course, you know, whatever, you gotta make sure that there's, in a fully determined universe, there's no reason to say that I am who I am because of my mother any more than anyone else. because everything's so completely locked in. And I think that that's just absurd. Obviously, the causality, you should be able to ascribe causality from things that are closer to you. But if everything's static, then you can't really do that. So I think that's one of the things that's lost.
Well, yeah, I mean, and just on a pragmatic level, you lose the entire legal system.
Right. Yeah. Well, I think that's a huge motivator for a lot of people. In my more masochistic states, sometimes I would used to listen to Sam Harris, and he would talk about this all the time, because he has this idea that free will doesn't exist, and he goes on and on about what the implications are for the legal system. He says, well, you know, we shouldn't put people in prison for that, but we should, you know, maybe keep them away from other people. And it's like, well, okay. But I think a lot of people who like determinism like it because it seems to them to be an understanding, a way of understanding and sympathizing with people who have done horrible things, or does that make sense?
Well, yes, I mean, not only that, but the whole idea of we seem to be living in an environment in which we have an excess of compassion for people who, for whatever reason, who don't have their lives together. I mean, Jordan Peterson would say, you know, you need to sort yourself out. If you're 40 years old and for whatever reason you haven't sorted yourself out, and therefore you're living on the streets, or you have a less than optimal job because you didn't stay in high school, we don't want to have to ascribe consequences to their behavior, because that feels uncompassionate.
Mm-hmm.
But I think we're approaching the problem from the back side. We should be doing is trying to go to the front side and help people to make better decisions when they're young, give them better educational guidance, and straighten out for ourselves what we mean by the good life, so that we have something to offer people to strive towards. Because if you start out at the front end saying, well, all of this stuff has no meaning, then you pretty soon end up living on the streets. Then it for sure has no meaning.
Yeah.
Everybody else is supposed to be compassionate towards you, when the real compassion would be helping you get off the street and helping you have a life of meaning. And we're just in an upside down world, you know.
Mm-hmm.
For
people like you and me who are artists, it always seemed, and I don't want to put this on you, but as an artist, as someone who values creativity, I never understood why people at all found determinism to be comforting, because from this side of things, the hope is that you can create something, and that artistic expression is meaningful, and I think that does require free will. I think that it makes other people anxious from, you know, the reason we just talked about, but they're kind of complementary, not necessarily complementary in the right way, but in a opposed ways of looking at things.
Well, one of the things that I think that he talks about in here, and that I've also heard, are you familiar with Stephen Wolfram?
Mm-hmm.
Yeah, okay. Stephen Wolfram has also talked about this, that I think really just puts determinism away. There's no way you can believe in determinism if you understand this principle. I'm going to bring up this little clip here. And I think if the physicists really paid attention to this, they would change their idea about determinism. I got the right spot there. 4230.
In nature, the fact that we all do seem to inhabit the same world.
I would say, I mean, maybe the best way to say how it's accounted for is to say what you call regularity. This is a kind of Bayesian idea. Things are similar to the extent that you ignore the distinctions. So how do you account for irregularities? You sort of squint your eyes and don't look clearly at things. You forget the details, or you say that the details are unimportant. So for instance, every snowflake has six-fold symmetry. So if you look at where the crystals are and you go around, you'll see that they point in six directions. But you know the old adage that every snowflake is different. So, oh, what's the regularity? Well, I'm going to ignore all of the differences in the snowflake. They're there, but I'm going to ignore all of those little unimportant things and focus on the big thing that makes them all the same. So I think ultimately all of the what we call regularities in the universe are of this variety. It's that we are consciously choosing to not focus on the distinctions. And therefore we start to say, well, this is similar to that. But that's a construction of the human mind. It's not inherent in the thing itself, because in the thing itself, in the qualia, all the distinct qualia in Donald's way of talking, or in the pure experiences of James's way of talking, everything in the universe is genuinely distinct from everything else. Nothing is repeated. And it's the...
Okay, now everything is genuinely distinct from everything else. Nothing is repeated. If he's correct, then the quantum physicists who are working on the standard model and insisting that there are only so many different kinds of particles and every charm quark is identical to every other charm quark and every up quark is identical to every other up quark, is running headlong into this thing that he just brought up. And I want to show you something from Stephen Wolfram. Wolfram does these things called working sessions with scientists from different fields because he's trying to figure out where things fit into his new theory of fundamental physics. And he did this working session last year in molecular computing. Every once in a while, I'll listen to one of these and I'll just have it on in the background while I'm cleaning house or something, and something will pop out to me. And I was listening to this one and this popped out to me.
Okay, so James's observation is that the proof of uniqueness of an Emes, of an atom of existence.
Now I have to explain here. In his theory, space is made up of atoms of existence, but he doesn't call them atoms, he calls them Emes because they're actually a lot smaller than an atom. They're actually a lot smaller than a quantum particle. So he has a word for them. He calls them Emes.
How do you spell that?
E-M-E-S.
Thanks.
Cannot be made in the context of the Rulliad alone.
The proof of the existence of Emes. Let's just go back here.
James's observation is that the proof of uniqueness of an Emes, of an atom of existence, cannot be made in the context of the Rulliad alone, but requires regression to the hyper-Rulliad. Okay, so
Just
The Rulliad is, roughly speaking, the universe in Wolfram's theory, and the hyper-Rulliad is that which is outside the Rulliad, because the Rulliad is based on rules. Those rules got to come from somewhere. So they're coming from outside in the hyper-Rulliad. So he's saying the proof of the uniqueness of Emes, because James has said every Emes is unique. And they're going to go on with this discussion.
For some context, right? So Emes have to, they possess two properties. So the first is that they exist, which is important. And the second is that they have UUIDs. Okay, they have to exist because if Emes don't exist, I mean, they're the primordial building blocks of the Rulliad. So if the Emes don't exist, then the Rulliad doesn't exist. But they also have to be unique, because if they're not unique, you can't distinguish between them. And I would say if you can't distinguish between the Emes, then there's no reason to say that there are multiple Emes, and then you basically have a big crunch in the Rulliad and the whole thing will collapse. So you have to have both of them.
You know,
yeah, go ahead.
Okay, so first point about the Rulliad is one of the key issues is, the Rulliad in its rawest state trees out everything. Okay, but there are equivalences which make the Rulliad non-trivial. Okay, but those equivalences we have said are, but those equivalences are being made by observers. I mean, most of the equivalencing is.
And what I take him to mean here is that he's talking in the same way that Christopher Fuchs was talking about the way we see snowflakes, or the way we see things in the universe, where we kind of ignore the differences and we see the similarities.
Yeah. I mean, and
this is Wolfram's idea that the observer is embedded in the universe. Therefore, even though the universe in general is computationally irreducible, there are slices of computational reducibility that are there because of the kinds of observer that we see the world in a certain way that allows us to develop rules of physics and rules of mathematics, and to see things the way we do because we are observers embedded in the universe. In other words, we don't have an outside view. We can't look at the whole universe and say, oh, it's this way or that way, because we are also part of the universe.
Right. And this is in all sorts of discussions that we're having in the corner, right? Mm-hmm. And I mean, it's, if you step back from it for a second, it seems, well, this is kind of a trivial statement, that things are similar to the degree that they're similar, and they're different to the degree that but they're ultimately different. And we kind of use our judgment to determine what's worth being called similar. But I don't think it's trivial. I think it's true, but I do think it's deep. And I like finding people who are talking about that. Again, it's basic, but I'd like to read more into Wolfram's description, because I haven't taken the time to do that yet.
You can get a pretty rough and ready idea of it just from his I'll put a link to his page. He's done really wonderful work of documenting everything that he's done. But I've also probably got half a dozen videos on my channel talking about it, and okay. Taking different aspects of the theory and looking at it from a lot of different angles. But to me, this thing about the Emes having unique user IDs, I mean, he said the Emes have UUIDs. Basically, what he's saying is that every Emes in the universe is unique. That's a huge statement to just kind of toss off in a working session, right? But they're thinking about that for a particular reason, because in his theory, he says, everything trees out. But what he means is that you start with one rule. We probably need to do this we probably need to have another conversation if you
Sure.
could be up for that. But I can show you really quick. We can show you really quick his basic concept. The visual summary here. So you can see this is kind of like a tree.
Mhm.
Yeah, so the basic idea is that if you take a rule and then when you apply the rule, the very first Emes, you have one Emes here, and then it has two options. You apply the rule and now you have this. And if you keep applying that rule over and over again, you start getting something that looks like these things.
Mhm.
And if you apply it multiple times, you start getting something that looks like this.
Mhm.
And if you take that apart and you look at it from the standpoint of when the updating events happen, because what he says is that space is made up of particles of space. So this first Emes is a particle of space, and then time updates events. So every time time updates, the number of particles grows. So time is in some sense growing space.
One of the hardest things to learn when you're first introduced to a new field with its new all of its new notations is what an arrow means. So, I'm gonna have to take a look at this myself and figure
Yeah.
out. I see two different types of arrows just in that one, well, maybe three, in that one little.
Yes, yeah, he explains the
But,
whole thing.
yeah, so I got to
it's way
figure out
more
what an arrow means before I'm able to comment much on this. But
well, there's also another guy who's actually doing videos, animation videos, explaining step by step how this grows to this, grows to this.
Mhm.
And I can link to that as well.
All right. Yes, please.
Yeah, it's good stuff. He's really doing a good job on this. But the point is that everything is treeing out here. And this means that the Emes, this is just all, like the whole universe is made up of these Emes of space, which have substance, that space actually has substance.
Mhm.
And that substance is ordered by the events of time, because each time time updates these events, then space grows.
Well, you know what, Lewis hated it when people called the trilogy the space trilogy. Do you know why?
No,
Because he said that makes it sound so empty. It's full. It's full.
Yes, it's full, it's full. And I mean, this is one of the things I like about Wolfram's theory, is that it may or may not be true, but the implications that are coming out of it are just very, very rich. I've certainly learned a lot from
Yeah.
it. And you've given me already an hour and a half, more than an hour and a half of your time. So maybe we can do this again sometime. It's been
That would be great.
fun picking your brain.
Thank you so much, Karen, and hope to talk to you more about art and painting and physics and Emes and all of that.
Yeah, sounds really great. Okay, have a great day.
All right. You
Bye-bye.
too. Bye-bye.